Okay, so in section 14.3, we're going to talk about another attribute of voting that requires some mathematics, and it's what's called apportionment. Now, you might never have heard this word. What apportionment means is it's a method to allocate a total number of objects. So where this came from, because in the history of the world, okay, not too many cultures and countries voted until the United States made it pretty prominent. Okay, and so a lot of the underlying current, a lot of the math behind voting and apportionment started here and spread out. So where this happened, so of course you learn by trial and error in these things. So where this happened is you have these states, right? 13 of them to begin with. You have these states, and you want to be able to give representation in a equal amount to the states. So that's what apportionment is. So like right now, why I don't know my civics, it's embarrassing, but why does Florida have a certain number of people in the House of Representatives, and Alabama has a different amount, and Massachusetts has a different amount? Where does that come from? And even within Florida, different counties and different districts, like, so it works its way down, but we're gonna think at the big level. So that's what we're going to be talking about, is the mathematics, the early mathematics. It's much more complicated now, but we're going to talk about the origins of this and how it works. So first, what we have is what's called the standard divisor. The standard divisor is the ratio of your total population to the number of items to be apportioned. So for instance, okay, congressmen, congresspeople, how many congresspeople a country decides they're going to have, okay, then gets divided into the total population. Okay, and that gives you representation. It tells you how many people in the population per representative. Okay, and we're going to do an example, put some numbers to this in a minute to make it seem a little bit. So here's how you calculate the standard divisor. You take your total population, and then you divide it by the number of items that are being allocated. Then from that, what you derive is what's called the standard quota. So then the standard quota is the ratio of a group's total to the standard divisor. So you start off with your total population. You say we're going to have this many representatives, and so then you say, okay, how many people per representative? And then you go through each state and you say, okay, this state has this many people, so we're going to say, okay, how many representatives then are they due? And again, we're going to put numbers to this to hopefully make this a little bit clearer. I know just putting formulas up here, that's devastating. So the standard quota is total for a particular group or state or something like that, divided by that standard divisor that you just found. All right, this is the exact number of items each group would be allocated, and we're going to see why that's a problem in just a minute when we do our first couple of examples. Okay, so our first example that we're each going to do is just an example to calculate these two things so that I can hopefully make it a little clearer, because I know at first it's about as clear as mud. I want to make it a little clearer what we're actually calculating. So here's my first example one. We've got an organization that operates medical clinics, and they recently hired 60 doctors. The number of patients served each week is given by the table below. Okay, so Clinic A serves 246 people a week, B 201 people a week, etc. All the clinics together total 1,080 people a week that come through the doors. So here's the premise about apportionment. All these clinics serve a different number of people. So we don't want to give them all the same number of doctors. That means some doctors are going to be working harder than others. They're going to be seeing more patients and some fewer. What we want to do is we want to make sure that it's as even as it can be. So the doctors are all going to be seeing about the same number of patients, whatever clinic that they are in. So what we're going to do is we're going to determine how to apportion the 60 new doctors to meet the needs of each clinic. Okay. All right, so then So what we're going to do is we're going to determine the standard quota. So the first thing we're going to do is we're going to find the standard divisor. I'm going to just abbreviate that SD because I'm really clever. And I'm going to put units on this so that you can see what we're doing here. So if you look up at the formula for the standard divisor, what am I going to have in the top? I'm sorry, what'd you say? Yes, 1,080. That 1,080, that's our population. And I'm just going to write, those are my patients, my patient population. And again, looking up the formula for the standard divisor, what am I going to put in the denominator of this? 60, because those are the items to be apportioned. Those are the doctors that I am trying to distribute to these 5 different clinics in a fair way. So I have 60 doctors. So notice what I'm going to get out of the standard divisor, this first thing. I'm going to say, okay, if I have 60 doctors and I see 1,080 patients, that means that I need a calculator because I can't do that in the noggin. So that's 1,080 divided by 60, that's 18. That means that there's going to be 18 patients for each one doctor. And we would just write that 18, but I'm just trying to preserve the ratio there so you can see what we just found. You take your total population and you divide by the number of things that you're trying to distribute. And so that gives me the ratio. I should have 18 patients for every doctor. Okay, so now what we're going to do is for each of the groups, we're going to calculate the standard quota. I probably should have written my standard divisor in a different place, so I'm going to use a different color. Wasn't thinking ahead. I need to learn to think ahead better. All right, so what I'm going to do is I'm going to list the standard quotas underneath each of these. So I'm just going to put SQ for standard quota. Again, I'm really clever. And what we're going to do for each of these is say, okay, if I have 18 patients per doctor, Clinic A has 246 patients. I'm going to take Clinic A's 246 because that's what this formula says to do, the total for a particular group, and you're going to divide it by that standard divisor. So I'm going to take the 246 divided by 18. So I'm just going to write that over here for Clinic A. That's 246 divided by 18. And when I do that, I end up with 13.666666. I'm just going to round that to the hundredths place. I think that's what our book and our My Math Lab likes. So I'm going to do 13.67. So I'm going to put that right here, 13.67. So what that means is if I have 246 patients and in each group of 18 patients gets a doctor, that's 13.67 doctors that I need to allocate to that. That's the exact number. That's what the standard quota gives you. What's the problem with that?
You don't have 0.67.
Yeah, you don't want to be that doctor that they're going to have to cut into thirds, right? That's going to be painful. Okay, yes. So that's that. You can't just do a straight division. That's the reason for the need for apportionment. Is I have to figure out what does that 0.67 mean. So go ahead for me. I'm going to do it. You work ahead of me because you're quicker than me. Go ahead now and figure out the standard quota, the exact number of doctors each of these clinics should get. And round to the hundredth, please. So all you're doing, hopefully, is you're taking each of the clinic's total patients, you're dividing each by 18, okay? Because each group of 18 patients gets a doctor. So that means when I divide 201 by 18, I got 11.17. So Clinic B should get 11.17 doctors. Clinic C, 196 divided by 18 is 10.89, so they should get 10.89 doctors. D, 211 divided by 18 gives you 11.72 doctors. And then Clinic E, 226 divided by 18 is 12.56 doctors. We doing good on the arithmetic? Okay, so I haven't apportioned anything yet. Okay, that's the exact math. And what we're going to spend the remainder of today and the beginning of tomorrow doing is we're going to go through 3 of the early methods of apportionment on how can I distribute to make up for those decimals. But before we do that, okay, we'll come back to this and we're going to help this clinic in just a minute. Exercise 1, you're going to do the same thing. A hotel chain needs to apportion 25 new staff members among 3 hotels in the same city. The company wants to apportion the 25 new staff according to the number of rooms in each facility. So determine the standard divisor for each hotel. So I'm sorry, not the standard divisor. That should be the standard quota. Again, good job, Perkster. You do need the standard divisor, but you use the standard divisor to figure out the quota, meaning how many staff people does each hotel get according to their rooms. So I'm going to give you 2 minutes to get a head start on this, and then we'll go. All right, so here's what I got, the standard divisor. The standard divisor, you got the formula right in front of you. The standard divisor is the total population, so I've got 675 rooms, and I'm dividing that among 25 staff. And so what that means, when I go ahead and do that division, what do we get? How many rooms is each staff member accountable for? What was that? 27. Okay, so 27 rooms per each staff member I'm hiring. Okay, so I want to know what's the implication for the hotel. That means each hotel is going to get how many. So I'm going to take each of these 306 divided by 27, round it to the second decimal place. So when you do that, 306 divided by 27, what's the result? 11.33. Do I have confirmation? Okay, so that's 11.33 staff members. Again, we have a problem. Okay, I don't want to be that one they have to cut in half. Okay, 214 divided by 27. How many staff members for that hotel? 7.93. Again, do I have agreement? We doing okay? And then finally, 155 divided by 27. How many staff members for that hotel? 5.54. Sounds good to me. So now we're going to learn how do I do this. So the first method that we have for this, yes? I don't know.
Right, yeah.
It should be 3, 4.
Yeah, I forgot because it's repeating 3 and I wasn't sure if there's need to be remember.
No, it's 306, right? Divided by 27.
Like
That's 11.33333. Remember, rounding is if the number after the 3 is a 5 or more, you would round up. So it would be 3, 4. So it's going to stay 3, 3. That's fine.
Sorry, I got nervous.
Okay, so the first method, there's going to be 3 that we talk about. There's lots of others, but again, I'm just trying to give you a little bit of an overview. The first one's called Hamilton's method. Now, this is not the same Hamilton from graph theory. This is actually the Hamilton from the Hamilton the musical, okay? One of the founding fathers, so to speak. So as they were trying to decide how to apportion things, this is the method that Alexander Hamilton came up with. So we're going to learn his method. When we come back next time, we're going to do Thomas Jefferson's method. And then I think Webster, but I don't remember which Webster, if it's the dictionary Webster or a different one. I'll have to look at. So we're going to look at the methods that these people developed way back when. So what you're going to do is this: to apportion items among the groups. The first two steps you've already done. You're going to calculate the standard divisor. Then you're going to calculate the standard quota for each group. We've already done that. Okay, so my example, I'm going to go back to the medical clinics, and we're going to figure this out. So then what you're going to do is you're going to round each standard quota down. When you do this, this is called the lower quota. Okay, when you round down, or you could call it just truncating, meaning we're going to cut the decimal off. So we're going to round each standard quota down to the nearest integer. So let's do that. So I'm going to flip back over to my example. I've got 5 clinics. Let me rewrite their numbers right here. I've got A and B and C and D and E. And clinic A was 13.67, 11.17, 10.89, 11.72, and then 12.56. And so step 1, or I guess it's step 3. Step 3 is I'm going to truncate each of those. So I'm going to say, okay, A, you were supposed to get 13.67 doctors. You're just going to get 13. Okay, B, you're going to get 11. C, you're going to get 10. D, you're going to get 11. E, you're going to get 12. What does that total up to? 13 plus 11 plus 10 plus 11 plus 12. That adds up to 57. Okay, so we've taken care of 57 of the doctors. And so then step 4 is, okay, I've got 3 doctors unaccounted for. So what we're going to do with those 3 doctors is you're going to look at the decimal parts, and you're going to give them to the ones with the highest, who lost the most, basically. So which one of the clinics lost the most when we truncated? C. C had a 0.89 right there. So I'm going to add one more to C. So C gets 11 doctors. Congratulations. I've got 3 doctors to hand out. Who gets the next doctor? Who has the next highest decimal part? D is 0.72. So D, you're going to get 12 doctors. Congratulations. Now I got one more. Who gets the last doctor? Which one? B is 0.17. So that's actually the lowest one. So we went 0.89, 89 was bigger than 72. And which one's the next biggest one? A. A is getting 14 doctors. And so then B stays at 11. It doesn't get one of the extras. E stays at 12. And then I always like to just make sure with my calculator that 25, 36, 48, 60. There's Hamilton's apportionment. Yes. Right. But so getting 12 for each, that would be, okay, I'm just gonna give everybody the same number. But what that doesn't account for is clinic A sees 246 patients a week and C sees 196. So now you've got these doctors working harder. They're going to be upset because they're going to want to get paid more. Okay, so we're apportioning things out in an equal manner. Okay, so great. That's a great question. Great observation. Now, what you'll notice, the flaw in Hamilton's method is, E says, hey, we've got 0.56. That's significant. You kind of cheated us. And so the next method, when we come back next time, will be Jefferson's response. So we're just going to have time. Well, we got 7 minutes. Do exercise 2. Use Hamilton's method for your 25 new staff members that are at the bottom of the previous page.
why we use the larger decimal. Makes sense?
Yeah, the premise here is when we truncated and got rid of the 0.89, C lost the most, right? 0.89 is pretty significant. That's actually close to 11. So since I had 3 more to give, I'm going to give C one of them. And then now that's why we go down. But then what you're pointing out is that becomes kind of part of the agitation of it is E's like, why don't I'm really close to 0.67. You didn't give me another doctor, right? Like, so that becomes the flaw to this and why a different method was developed. Okay, so we're going to use Hamilton's method to apportion the 25 new staff members to the hotel. So the first thing Hamilton's method says is just truncate. So A gets 11 staff members, B gets 7, C gets 5, and that is, what's that, 18? That's 23. So how many staff members do I have now to dole out? 2. Who gets the first one?
7.92.
Yeah, B gets the first one. That's 0.93. That's the biggest decimal part. So I'm gonna give that 8. Who gets the next one? 0.74 is the next biggest one. That's 6. And then since I only had 2 to give out, A is gonna stay at 11. And so that turns out to be 25. So there's my Hamilton apportionment. Okay, we've got 4 more minutes. You got time to get a good start on this. We'll start next time with exercise 4. Exercise 3, what you're going to do is just go through the whole process. You're going to calculate your standard divisor by taking the population divided by the 150 legislative seats. And then you're going to see how many legislative seats for each of the 4 states. Then you're going to do Hamilton's algorithm. All right, just for time's sake, I'm going to get started. Keep doing your work. Check your work with mine. And here we go. I'm going to calculate the standard divisor first. I'm going to take that population, divide it by the number of legislators. And so that gives me, and you, $50,000 people per legislator. Okay, so now what I'm going to do is I'm going to take each of these states' populations and I'm going to say, okay, how many legislators does that mean? So the first one, 1,220, divided by 50 is, they should get 24.4. And 2,730, divided by 50,000 gives me 54.6. 857 gives me 17.14. And then finally for the last state, divided by 50,000. Okay, so once you get done with the busy work, Hamilton's algorithm goes really quick. So here are my quotas. Okay, state A should get 24.4, state B 54.6, state C 17.4, state D 53.86. So again, that's not going to work out. So I need whole numbers. So what we're going to do is we're going to now reduce these. So state A, I'm projecting you to get 24, state B 54, 17, and 53. And when I add those up, does anyone have that far enough? How many is that?
148.
148. Okay, so I have now, is that 148? 8. Oh yeah, it is because I'm trying to add and talk at the same time. That's a disaster. So I have 2 more that I have to add back in because we have 150 representatives. So the first one I'm going to give to state D, move them up to 54 because that 0.86 right there. And then the other one's going to go to state B. I'm going to move them up to 55. Because of the 0.6, the other 2 are going to stay at 24 and 17, and that's going to add up to 150. So where we will start next time is we will start with exercise 4 just to review Hamilton's algorithm, and then we will move on.